Welcome back to our series on applied regression analysis. I'm Mark Ledbetter, and this is a video for chapter 16 in the textbook, which is called model selection for regression and how to choose the best or select the best regression model from the list of variables that we have available. And this is a data mining technique. So for those of you who are interested in data science, this is a very valuable data mining technique that is used very frequently. Okay, so I've included some extra things in this code that I'm not using, but some of you who are in the class know that I've already discussed. If you want to use advanced techniques in R Markdown or RMD, you need to install tiny text, and this is the code to do so. And then this code, after you have installed it, will check to make sure that it's successfully installed. It will give you a true. The reason I'm not using the advanced techniques in this is because if I do, then up here I had a statement that linked to a TEX or tech document that set some advanced settings and allowed you to do some fancy stuff, and it's very handy. The only problem is you either have to put that file in the same directory with where you're going to create your R Markdown or where you have your R Markdown every single time, which makes distributing this much more difficult. So instead of doing that, I've removed it so that we don't have to worry about the code crashing or not working because it's missing that preamble text for those advanced techniques, which I really don't need in this document. Okay. So let's get started. Now I have run this code already, so you'll see that my the messages here are not showing up, but I have changed this to say include equals true, so this will be knitted into the final PDF, but message equals false means that none of the messages that show up in red will be in your document, and that shortens your document and makes it look more professional. Here the R setup with this that we're really not using, I've said include equals false, so it does not show up in the knitted document. Okay, so I'm including a new package, ordinary least squares regression, and I forget what the second R stands for. So if you haven't used that before, you need to install it. You can either use the install.packages, of course, or you can come up to Tools, Install Packages, and type in OLSRR and install that way. But you definitely, either way, you need to still call the library on OLSRR, and we're going to use that extensively. Now, I've also put \v space and then how much of a vertical space you want. This works well in R. I've tried H space, which is a horizontal space, and it does not seem to work. Okay. So we're going to use problem 1 from chapter 16 as our example. Now I have provided a student file, which is a very reduced text version of this file, because really I'm wanting to give you the code to use the methods, and then you need to come up with the text and what have you to talk about it. I don't want you copying word for word what I say. Of course, that's plagiarism anyway, so we don't want to do that. Okay, so these data from question 1 in chapter 16 are hypothetical. That was interesting. I didn't realize that they were hypothetical, and results of measuring a response variable, weight, and predictor variables, height and age, on 12 children. So n equals 12, our sample size is 12. And we are going to add age squared, height squared, and age times height. I'll get rid of that, just age height, or age times height as the interaction term there for this analysis. It says to using the available regression program, for us that's R and RMD, and the accompanying computer output from that, determine the best regression equation relating weight to the 5 independent variables as follows. First, use a forward approach, then a backwards approach, then stepwise, and then they talk about something called a, in this case it's a 2-stage approach. Now, there are many variants of a two-stage approach or a multi-stage approach. You can use more than two stages. What you usually do is in one stage you either set a you determine that these variables are going to be in the model no matter what, or as in this case you say, okay, let's see if any of these variables go into the model first. And then any variables that are selected in that first stage, we keep them through the second stage, and we repeat the process with either different variables or higher powers or interaction terms, and that's what's happening here. We're going to start with the single variables, all of them, age and height. We're going to look to see if either or both are significant if we add it to the model, and then once we've determined which single variable to use, we will go to and look at the powers and the interaction term to see if any of those should be added to the model that has these from the first stage. Okay, so we'll see how that works when we get there in case it's not clear right now. And it says to use alpha equals 0.1 as our criteria for adding these variables to the model. And then we're going to use the all possible models approach last. I've also put this new page, backslash new page command in there that will determine, so everything beyond this will go to the next page. It's a page break basically. Now, you don't want to leave this in the same place all the time. You'd want to knit your document, take a look at it and say, well, it'd be better if I put a new page break here so that this information is together. So this is just another formatting tool for you. So you can take it out or use it as you like. Now we have our data set that I've copied over from Excel and formatted nicely. So please do the same. Please format and line everything up so that it's easy to read. If you do this, then there's usually not a reason, since this is included, there's usually not a reason to actually print out your data. Okay? I print it out when I'm debugging or when I'm first doing it to make sure that everything is as it's supposed to be, and then many times I will comment this out. Okay? So let's run this chunk. And now we're going to look at, we want to choose a maximum model. That's the first thing we need to do when we're doing this selection methods. So, and we've been told what to use as our maximum model. We want height, we want age, we want height squared, and age times height. Okay? And so we are also told to use the p-values, which in the book comes across as f sub p. Okay? So, and again, I say, well, we're saying we're using the f, but we're really using its p-values for the coefficients. So first is the forward selection. We're going to select a model based on the p-values in a forward direction. The default threshold for p-values in this model is 0.3, and this is much too large in most cases. So a very accepted value for this is 0.15, and so we have modified that. Now, I've used p-enter because that is the parameter in the function. So here's the full model. So we've put everything in here, all 5 variables. Make sure you put the data frame where it's located, or else it doesn't know where it's located unless you have attached the data frame. And attaching the data frame is either frowned upon or encouraged depending on your field of thought there. I discourage it because if you forget to detach it, then you're making analysis that you didn't mean to make. So you have to be very careful when you attach a data set to make sure that you detach it when you're done. All right, so here's the full model. We don't need the null model here, but I put it in anyway. And now here is our forward selection code. We have quite a few codes, or quite a few functions that we're not going to use that are available. So in this book we focus on the p-value, but it's not the only method. So this says OLS, ordinary least squares, step, forward, and then the method, p-value. So by underscore. I could change this to AIC. That is another function that's available, and then instead of selecting by p-value, it would select by the Akaike information code, which I probably said wrong. Okay, so here's our full model. That comes first, and my computer mouse has been acting up all day, so maybe I need to change the battery. It does weird things in the middle of my selection. All right, so full model, comma, and then this progress equals true. Let's take a look at the help here and say OLS step, and I want forward. And so it says that the progress here is, if true, will print the regression result at each step. No, I'm sorry, that's details. If true, will display variable selection progress. So I definitely want that. Okay, so let's run this chunk. I'm also going to take out some extra lines of code here. So let's run this chunk and see what happens. So we have our forward selection method. It gives us the candidate terms, and it tells us we're selecting based on p-value. That's very handy. And step one, it added age and height because it had the lowest p-value below 0.15. It's given you some summary here. The adjusted, or R squared, adjusted R squared. This I'm not very familiar with. You don't want to use this predicted R squared unless you're familiar with that specific program, and I'm not. Here's the root mean squared error. That's a good value, and again, I'm not real sure what just happened to my mouse. Okay, here we go. So there's a root mean squared error, and we have the coefficient of variation, MSE. That is correct. The MAE stands for the mean absolute error. So that's not a measure that we've used in this class. I believe we did talk about it. And that's where you take, instead of yi minus yi hat quantity squared, you take the absolute value of yi minus yi hat, and then you add those up. Okay, so it gives you a little different measure. Now, we have our ANOVA table. So this is the reason we didn't need anything fancy, because it's given us a nice ANOVA table in the format that we like. Okay, and it's telling us that the significance is 0.0003, which is very low, which is very highly significant. And then it tells us our parameter estimates for the intercept and for age and height, that interaction. And it's not very highly here. It's not, oh, this is an upper and lower. Good. This is the upper and lower confidence interval. I was looking at the wrong thing. Our significance levels are here, and it only rounds it to 3 decimal places. So highly significant for both, which is good. Now it says no more variables to be added, and that's what we saw before. And then it gives you the final model output, the summary, which is nice to have, because you're seeing at each step all these different outputs, and it's nice to have the very final model at the end, so that the first thing that you see when you scroll up is the final model output. Now in this case we only had one step, so it really didn't make any difference. Okay, so our model, just as we saw in the book, includes beta naught plus beta 5 age height. You'll notice that I'm using a 5 here because that's what I used in the full model when I specified the full or maximum model to begin with. Once you assign a beta number, a subscript to a beta that with a variable, it needs to stay the same throughout that analysis. So beta 1 in this analysis always goes with height. Beta 2 always goes with age. Beta 3 always goes with height squared. Beta 4 with age squared. And beta 5 with age times height. Otherwise, you're going to confuse your reader, and it's not the convention. The convention is to keep these constant and assign to the same values throughout. So that's the reason that I have beta naught plus beta 5 times age height, and then of course epsilon. Okay, and we've mentioned before that this violates the hierarchy principle. Okay, so now we do backward selection. The code here, OLS step, now the only thing difference is instead of forward, Sorry about that. So instead of forward, we have backward here, and then P, and everything else is the same, except now instead of P enter, I have P remove, because we're doing backwards elimination. We're removing variables from the model, not entering them in. So instead of P enter, we have P remove, or PREM. And that has been set to 0.15 now. So when we run this code, we get a lot of output, and we're getting a lot more output because we have more steps. Because with backward selection, we start with all 5 in the model, and we keep removing until we get to the bottom. So one way to get to the top of this without scrolling, which is very fast, is see my mouse or my indicator is here, and I just up arrow, and it takes me to the very top of the output. So it tells us it's backwards elimination, gives us the candidate terms or the variables. We're eliminating based on p-value. That's very nice. And so the first one that's removed, x for remove, is age squared. And so this is the backwards elimination, step 1, variable age 2 removed. It gives you the model summary statistics, which I don't really need. And interestingly, it tells me the significance level of the model with 4 variables in it without the age, okay? So without age squared. So it doesn't tell us the model with age squared, it tells us the model after we removed age squared. And so we have the significance level of all of these variables. And what we're going to do is choose the highest p-value next. So 0.825 and not the intercept. The intercept stays in unless you run a very special program, and I didn't see a place to remove it in here, but you might be able to if you look at the documentation for these functions. Okay, so the highest p-value, which is 0.825 amongst the variables, gets removed next. So this would say that age is going, yes, age will be removed next. Here it says removing age next, variable age removed. The summary of the remaining model, it's highly significant, more highly significant than it was. It was 0.01, now it's 0.003 overall. And now we look at the significance of what remains, and the next highest p-value is height squared. And so height squared is removed. We come down, we again have the model summary statistics, we have the ANOVA table, and we have the parameter estimates, and we look at the significance levels here, and we see that height has the highest p-value amongst the variables left, not the intercept, and so height is in fact in step 4 removed. Again, the model summary statistics, the ANOVA table, now we're down to 0.0000003 or 0.0003, so 4 decimal places. Both the intercept and the age times height are highly significant. So up until now, the intercept has not been significant in any of the models, I believe. There's 0.1, here's 0.4, here's 0.45, and that's it. So now that we've removed all but one of the variables, it's highly significant. Of course, again, we get this model with the interaction and nothing else, and so really, and it tells us no more variables satisfy the condition of p-value equals 0.15. So it has to be, that's a maximum value. So whatever you set it to, it's going to print it out here. Okay. So it then gives you a summary, variables removed in order, and then it gives you the final model output. Here are the summary statistics for the final model. Here's the ANOVA for the final model and the parameter estimates for the final model. And then it gives you elimination summary, and it says at which step, which variable was eliminated. And that's very nice to know and very handy to know the order in which they were removed, etc. Okay, so again, we end up with the same model, which still violates our hierarchy principle. And now we look at stepwise selection. So we're going to do stepwise selection And I don't know why that's showing up there. Okay, so we're going to do stepwise selection. So that means we're going to look at putting the most significant variable in first. Then we're going to try to put the next most significant variable in. And when we do that, we'll make sure that the previous variables that are put into the model are still significant. And if they're not, we'll remove the worst one. And then we keep doing this. It's like a forward step and a backward step and a forward step and a backward step. So we do that until we don't add any more. And it's going to be very short for this, but here is our function. And now instead of OLS step forward or backwards, it says both, and P again for p-value. And the full model is the same, but now we have both P enter and P removed here. And we also have still our progress equals true and our details equals true, so we get all the printout. Okay, so we're going to run this. Okay, so the stepwise, again, the candidate terms, remember we're going forward. It says in p-value is our criteria. Step 1, we add age, height, and with that, we end up with this model. And then it says no more variables to be added or removed, so it repeats all this with the final model output. And then that is it. So again, we end up with the same model as we did in the other two steps. Now remember that each of these different strategies, forward selection, backwards elimination, and stepwise selection, you can end up with 3 different models from these. They do not have to be the same. Okay? So just want you to be aware of that. Even though we ended up with the same one each time, we don't have to. Now we're going to look at this 2-stage selection. In this approach, we're going to consider several stages, but the book has really said use 2 stages. Use height and age, and unlike the notes, I'm doing this the way it should be done. So this is going to be different than the notes in the tech in the videos. Those were done using convenient methods, and basically it was variables added last, but it was to the full model. So that's really not the best way to go. So again, it told us to change P removed and P, yeah, if we use stepwise, if we use backwards, we're going to use P removed equals 0.1, and if we're using stepwise, P enter equals 0.1. Okay? So stage 1. In stage 1, I'm making a linear model object, height, age, and I'm putting in both height and age, and then I'm going to use stepwise to determine which one of these, let's see, so I have P enter 0.5 and P remove is 0.1. So I can enter it at 0.15, but if it doesn't stay, let's see, so that may not make sense, but actually you could enter it at 0.1 and remove it at 0.15. That would make more sense, but they said to make sure that it was in there, it's removed unless it's 0.1. Okay, so that's what I've done. We'll run this chunk, and it's stepwise. So just for 2 variables, height and age. So our candidates are height and age, p-value, step 1, add height. Here's the model summary, the ANOVA, it's significant. The intercept is not, but the variable is 0.001. Then we add age because it's significant, and we see that this model is highly significant. And we look at the significance levels, and height is 0.02, age is 0.056, but the intercept is still not significant. Again, we don't remove the intercept unless we have a very good reason to do so. It has to make practical sense, and that it goes through 0, 0, or in this case, because there's 2 variables, 0, 0, 0. All right. So here's our model summary statistics and our ANOVA and our parameter estimates of the final model. Actually, no, this is still, let's see, is this step 2? Yeah, so step 2, we have this, and so it looks like there's duplicates here. So model summary, ANOVA, parameter estimates with both, model summary again. Are these the same values? Looks like it. So for some reason this program has a duplicate. That's lovely. And then the same values here, and then again the final model output. So you can get a lot of output with this one. Now, oh, and so for the first stage, we ended up with height and age. Now for stage 2, the remaining variables are going to be tested one at a time. Okay? And the variable with the lowest p-value that's below the threshold, which is 0.1, will be added to the model next, if at all. I think I know what's happening up here with this. I think what happened is because I put 0.15, it goes in and then gets taken out. So let's change this to the same one and see if it still has the extra output. It looks like it may, so it may be a glitch in the programming. So there is adding height, there is adding age, the summary, and then it goes over it again. Yep, so it's got a duplicate in the, and then we do the final output here. Okay, so let's look at this stage 2. So what I've done is I had to write the code myself because I didn't really like any of the functions that I found out there. I wasn't real sure. Either I couldn't get them to work because they gave errors, and they seemed to work with the examples that I found on the internet, but not with any other examples. So that means that I don't want to use that function. So stage 1 variables I've defined here, height and age. Now this would be defined on the variables that are actually included in the model. And so in this case it was both of them. Now stage 2 are any other variables I want to consider in addition to stage 1. So here what I've done is I've said, so there's 3, and this is just for debugging, changing, you see it's commented out here, the I. So what I did was I wrote a loop, 1 to the length of stage 2. Stage 2 has 3 in here, so it's going to go I equals 1, I equals 2, I equals 3. And then I put the model for stage 1 here. So this has to be manually done each time. So this is not very efficient code, but it does work. And then what I did was I said, okay, I'm going to paste 0, which gets rid of the quotation marks. And I've got the plus here, and then I say stage 2i, so the first one's going to be height squared, and then collapse, that tells me that I don't want to put anything in between these two things. I just want to put them together. I already have this plus here, and so when I put I equals 1, first I need to run stage 1 and stage 2. Now when I come down here and I look at stage I, that's going to be height 2, as you can see here. And so if I run model 0 here, then it gives me the model that I want. And so I'm passing that to LM height age plus. So each time it goes through the loop, this gets redefined. And so I am pasting 0 to get rid of the, so that means that it doesn't have the quotations when it's passed. Model 0, collapse again equals empty, and data equals df1. And I have to put data equals df1 because otherwise it doesn't know what data set. And so when I run this time, you're going to see that this is a LM, and it has it just gives you this. But when I paste this here and look at what it's being passed, its weight is height equal to height, age, and height squared, which is what we want. And so it prints out a summary of the coefficients. So I've limited this to the coefficients so I don't get a lot of printout that I don't want. So here I see the coefficients, I see the p-values, and I see that height, I can look at this manually and say this is not below 0.1, so I'm not going to enter this one, but I'm going to do them all. And so here is height 2. It's not significant. And notice that it's by itself, height, age, and height squared. And height squared wasn't. Now age squared with these other two, it's not significant. And notice by putting it in this case, This one is above 0.05, but just barely, but this one is no longer significant, and this is still not significant. I put in age squared, add that to height and age, and it makes, now age is not significant, but height is. And then the intercept is less significant. And then I put in age times height with age and with height, and none of the variables nor the intercept are significant. So this is not a good model. So looking at this, once I have height and once I have age in there, which is the proper way to go, then none of the other variables improve the model. In fact, they make it worse. So we keep our model here with height and age, and this is a proper model, and this is the model, the best model, I would say, and this is the model we should use because it doesn't violate any of our rules or conventions. Okay? Now, once you have the final model, I found out that this, if you want a nice summary, instead of using ANOVA, that function, we can use OLS regress, and so I've passed the LM height age, so the linear model for height and age that we defined. Whoops, it's going to be easier for me to do this. So here is LM height and age. Weight has height and age as the predictors. Okay, let me step down below that, and we'll come back down here and we'll run this. And when we run this, this is what we get. So we get this nice model summary that we've been seeing, the ANOVA table, which is in the proper format, and the parameter estimate. So this is a very nice printout. Okay? And finally, we're going to do all possible regressions. And so I have to caution you that when I started looking at this, I realized that the F value and the MSE values are not the F and MSE values that we have been used to seeing. They're, again, for this advanced called general linear models, and it's doing some validation and I believe bootstrapping, and so that is not something we've discussed in this class. So these are not the variables that you know how to interpret, so please don't use them. So I've modified this to make it work for us, and so what I've done is I've still got the full model. I had to, well, let's see, so I don't think I need this anymore, but I'm not sure. Yep, no, I don't think I need that anymore. So I redefined it. Let's make sure that everything runs. Yep, everything's fine. So I was trying a different package and it required me to do something. So 1, 2, 3, 4, 5. So I don't need to redefine this. So I'll make sure that that's not there. Okay. So what we have, what I had to do in order to get things to print out the way I wanted to, I had to do something very convoluted. I believe it's because the person who made this function called OLS step all possible, so this gives us all possible regression models. It just prints out a few of these things and not all of them, but I saw that they have 14 different predictors. So unlike in our textbook, there's a lot more criteria that we can use here. What I didn't see was PRESS, okay, P-R-E-S-S. But there's quite a few of these. So in order to see the 14, if I just went here, then when I printed this out, I did get this, okay. But if I went to, let's see, if I went to plot it, I think I forgot to plot all possible. Oh, it doesn't like it. Okay. Well, that's a good reason not to do it. Okay. So anyway, I had to do this kind of convoluted, oh, that's right. So this is what happened. If I just run this function, OLS step all possible full model, then it only gives me 3 of the criteria, yet there's 14 in there. I wanted to see the others. So in order to do that, I had to, they were hidden, so I had to take this full model, and then I called and I said, I just want the column that's named MSEP. And I found out about MSEP through the documentation, the help file on this. And it told me, it listed a bunch of these things out, saying that these were outputs, but I wasn't seeing the output. So the only way to get the, that I could see to get that output was to do this. I did a column bind or C bind, and I put the whole table, and then I bound it with in columns with one other or one of its own variables to the end. And when I did that, so when I run this, and then again I print it out, now I have all of these variables here, and I have this that I added to the end, but this is MSEP, and you can see that MSEP is here, so I don't need it. So my next step was to only include columns 1 through 14, so that eliminated column 15 that I had added. And now I rename the column name so that there's something pretty, and then we print them out, and so now they look nice, and we can look through all these and use which ones we want. Okay. And so again, this may be too cumbersome for you. So we could just look at, because what you're getting here is you're getting 31 rows and all of these 15 variables. So if I come back here, we have the column, this was the original order for some reason, and then we have an index, and then we have, which is a row number, and then we have n, which is the number of variables in the model. So we start off with one single variables, and then 2 variables, 3 variables, down to 4 variables, and finally 5 variables, just like we had in our notes. But that's a lot of information. It doesn't print out nicely. So here we can look at just one at a time. Here's the single, here's the 2, 3, 4, and 5 variables. But again, this has 15 different columns, and so it wraps around and it doesn't look that pretty. You'll see when you knit this that it doesn't look so great. Now there's another way that we can do this. We can pull out those columns that we want, and they do not have to be beside each other if we use this method. And this is just one method. There's actually 2, but I won't go over the other. So I'm calling all possible. I'm putting a comma so that in the bracket so that I want all rows. And then I'm telling it which columns by name using C. So the concatenate. So C of, I want index n, the predictors, I want R squared, adjusted R squared, and malloc CP. The trick is that I named it this, and in order to call this, I have to use exactly the right notation. It has to have the period here, it has to have the capitalization in the right spot, spelled right, or else it won't pull it up. So here's what this looks like. And so I was going to originally include the same 3 criteria as the example in our notes, but that included the MSE, and the MSE here is not the same MSE. So I thought that it would be better for me to show R squared, adjusted R squared, and malloc CP. Okay, and then this will print out much more nicely when we knit this. So so that was there, but again, this is all 31 rows. You may want to break it down by the same predictors, but only one, looking at the different types of, or the different sizes of models. So here's just 1 variable only. Here are 2 variables only. Okay, there's 10 of them. There's 10 of the 3 variables only, back to 5 of the 4 variables only, and 1 of the 5 variables. So how we get the number of these is there are 5 variables total that we're choosing from, and here we've chosen 1. So 5 choose 1, if you know your combinatorics or combinations, is 5. 5 choose 2 is 10, which is equal to 5 choose 3, which is 10. And then 5 choose 4 is 5, and 5 choose 5 is 1. There's one way to choose all 5. So that's it for this code. I hope this gives you enough to get through it, and I'm sorry it took so long, but I just want to make sure that I explain everything. Hope you have Good success with your homework and your projects.